Alright guys, welcome to this stream. In this stream we are going to build an image classifier which will classify different chess pieces. So for this project we are going to use this dataset, chessman image dataset from Kaggle. And for the implementation part, I will be using FastAI library. By the way, I am going through this course. So the purpose behind this project is to implement all the things that I'm learning in this course, which is deep learning for coders from FastAI. I will be using Google Colab to create the project. So let's start up a new notebook. Let's call it chess piece. Chess pieces. Let's download the dataset now. Okay, the dataset has been downloaded. Now to use that dataset inside our Colab notebook, we have to upload that dataset to Google Drive. So let me do that. Okay, let's first extract the zip file. So while it is uploading, let's set up the notebook to use the FastAI library. These three commands will install and import the FastAI library and all of the other tools that we need to implement this project. We also need GPU to train our models. So let's select it from this menu. Alright, so now it is asking us to connect our Dropbox, Google Drive account. Okay, the data set has been uploaded as well. Now let's import fast. We will also be needing the widgets. Now that we have connected the Google Drive account to Colab, we can access the dataset that we have uploaded to the Google Drive. It's inside the dataset folder. So this is the dataset that we have uploaded. Let's fetch the images from the directory. Now let's create a data block from those images. Let's call the data block as chess. So data block basically it segregates our images based on the categories, and it splits images based on this argument and also transforms it. Data block API is provided by the FastAI library. Let's get image block and category block. Get the image file. And for the splitter, then we will be using random splitter, and we will keep 20% for validation set. So get y basically fetches the labels. So for labels, we will be using parent label function, which I guess it gets the parent folder which contains the images as the label name. So if we look at our data set, we have different pieces inside different folders. Suppose for queen, we have a different folder, for and so on for all the other pieces. So the parent folder is the label. See, the parent label basically fetches the parent folder name. Item transform. Let's keep the default as 128 for now. Okay, so now we have a data block. Let's get the data loaders. We have to provide this path argument to get the data loaders. And if all went well, we will have it inside the batch. Alright, so we have the images now, and as you can see, they are all resized down to 128 by 128 pixel. So the validation patch looks alright. Let's also check the training patch. Do we have training? Okay, we have train. Alright, so the training data set also looks correct as well. So what this code is doing is basically they are trying to apply different transforms and data augmentation to this training set. We are going to go with this transform. We'll apply randomized resize crop, which will resize our images to 224 by 224 pixels. This org transforms does this kind of thing. It rotates, it blurs, it sharpens the image sometimes. It squeezes it from one side and uh, stretches it from different side. Let's get a new data loader based on the transformation we applied just now. Okay, we have got the final data loader now. Let's use the CNN learner. Let's pass the data set, and let's also pass resonate 18. So basically we are doing is we are using a technique known as transfer learning. So we'll be using a pre-trained model, which is a resonate 18, which is trained on different images, but we will be using that model to fit to our needs, that is to classify the chess species. It is CNN CCN. Okay, so the model has been trained, and let's see, let's check how it is. So it is classifying lots of images as false positive. So it is classifying 6 queens as king. It is probably because our data set is too small. Let's check the top losses. Alright, so it is because this thing doesn't really look like a chess piece. It is a chess piece, but it looks like from a fancy chessboard. And this thing, it's a queen. Wait, is it a queen or it is saying that it is a bishop, but it is actually a queen. This is pawn, but it is saying it's a bishop. Let's check some more top losses. Let's check 15 top losses. This is classified as a king. Uh, this doesn't really look like a knight, but it is saying that it's a knight. And this image has been classified as rook because the top portion which can be classified as a king has been cut off from the data. So what can we do to improve our results? We can also remove this kind of noise, inappropriate images from our data set. Let's try to run it for 8 epochs. We only have only 556 images. Let's check if they have any other data set for chess PC. Chess position. This dataset contains 162 files. Running it for 80 Fox didn't really improve it very much. Let's plot the new confusion matrix. It seems like it did improve. Let's check the top losses. It is classifying in total 5 queens as kings. Let's remove this noise. So FastAI library provides this kind of widget to clean the data. Let's get the widget. It will show us the top losses and ask us to perform operation on these images. So from here we can either keep it or delete it or classify it as different image. So what this will do is it will move it from one folder to another folder. These are all the bishops. Most of the queen, it is confusing most of the queens to king. So let's try to remove. Let's try to clean the queen data set. Also check the king data set. This image contains other pieces as well. So I guess we should delete this image. Let's delete this one. And this image contains both a pawn and a rook, so we should also delete this one. Most of the queens are also confusing. See, this queen is classified as a pawn, and this queen also is classified as bishop. This queen is classified as a king, and this queen is also classified as a rook. remove this one as well. My laptop is running very slow. We flagged this one as delete, but I didn't keep it. First, first year includes a handy view for data cleaning that allows us to choose a correct category and the training was device sources along with the menu to allow images to be selected. Let's first of all check if they are being flagged or not. This one, suppose if we keep it as click. So once we change the menu, the selection vanishes. So for each category, we have to run this code. So let's try to run it for pawn. And let's delete this one and delete this one as well. That will be it for pawn, I guess. Right, let's run this code. We don't have to run this code because we didn't change anything in this set. So this for loop basically deletes the images which are flagged for deletion, and this for loop will move the images that are classified incorrectly in our dataset. So if a if a queen is placed inside a king folder in the dataset, it will try to move it based on our selection. So for this pawn dataset, we have not flagged anything as a different category, so we don't need to run this code. We can just run the cleaner.delete code. So now it should have deleted this one and this one as well. And let's check. Let's change the category and check it. My laptop is eating up a lot of memory, probably because of all the tabs I have opened. What happened? No such file automatically. Okay, it doesn't show us this image because we have deleted over here. So now, what if we run it again? Because we have deleted the image, we don't get it. So I guess after deleting the image, we have to run the model again or what? Maybe we should run the model again, then that code will work. Even this code is giving us error. No such file. Wait, did we delete the whole folder or what? Okay, it is there. Alright, I get it. We have to get a new data block as well. Now this code will run. And I think we don't have to fit the model again. We can directly get the images now from the cleaner. Okay, so after this model is done running, we will save this model. It will save us some time. We won't have to run it again and again. Also, this Google Colab sometimes disconnects automatically, so it's better to save the model, or we will lose the model. Let's let it run. Our model is not that bad. It is showing us 0.23% error rate. It is not bad, but we can improve it. So let's see. So as you can see, wait, where's the pawn? Okay, this is the pawn category. Okay, so those two pawn images that were incorrect has been deleted from the dataset. Let's quickly export the model. Let's call it chess1.pkl. So now we have the pickle file. Let's continue with the data cleaning. So among the top losses in the first row, 3 of them are pawn. So 3 of them are pawn and 2 of them are bishop. And this bishop does look like a pawn. This doesn't really look like a queen. Because this patterned edges are not visible, this doesn't really, this image is not very clear. So I guess we can remove that image. Also, this image contains a black background and the piece is also a black, so the features are not really visible. Okay, so this piece has been cropped. That's why it has been flagged as a bishop. This has been cropped as well, but still it doesn't really look like a queen. This piece is also not that much clear. I guess we can remove this one as well. So far it's not so bad, so let's try to check it. Let me download an image of queen. get the image that we just uploaded. So this is an image of a queen chess piece. Let's see how our learner predicts. Alright, we have to provide the path, not the image object. Alright, it is classified as a knight, which is incorrect. Anyway, this is an exotic piece, so let me download another image. See if this gets classified correctly or not. Alright, so it is being classified as a king. And of course, that's the case because we have only so many queens. 6 plus 7 plus 1 plus 2. We don't have that many queens, and most of them, almost half of them are being classified as a king. So that's why it is showing us king again and again. Most of the other pieces are performing fairly well. Only the queen is, maybe we should add some more images of queen. Let's see if we can do something else to improve our model. Let me check the notes of the FastAI course. Pets versus breeds. Okay, what is resizing? It's doing crop on the original image, and of that crop do a randomized crop and augmentation. Well, this technique does look promising. So this two lines does resizing. If we resize it to 460 and apply the augmentation transform and give it size set to 24 and minimum scale of 0.75. Okay, what does this minimum scale do? Let me check this notebook. Min scale, here where we place resize with randomized side crop, which is the transform that provides the behavior we just described. The most important parameter to pass is min scale, which determines how much of the image to select at minimum each time. Alright, so this does seem like an important parameter to set for our model, because that will determine how much of this image has been selected for training. As you can see, most of these images are being cropped from the top, which loses all the necessary features. So maybe we can pick something. Let's apply this same data augmentation and resize transforms and get a new data block. Randomize resized crop, and we are not doing randomize resized crop over here. Okay, let's roll with this one anyway. Let's copy this to transforms. Let's fit the model based on this new transform. Training loss did decrease, but the validation loss remained almost same. Let's plot the confusion matrix for the new model. It seems overall I didn't improve our model that much. Let's anyway export this new model. Resized. Let's see our new model detects this image or not. No, it is still detecting as a night. Let's plot the new top losses. Resized. Oh, great. Resizing does a lot of bad thing to our training set. In this case, it removed all the necessary features, and it did the same thing for almost most of these images. Can we use a randomized resize along with precise? Resizing is a way to is designed to minimize data destruction while maintaining good performance. But it seems that it is destroying the data in our case. In lot of the images which are in the top losses, it has destroyed the necessary features. While when we didn't precise it, they were still intact. All of the features were still intact. Only some were cut off, like this one, and this one. But in case of precising, it is cutting off a lot of data, like this one, this one, this one, this one, and this one. What if we just run it for 4 cycles? Let's run it for 4 epochs only this time. So it seems that running it for more than 4 epochs increases the validation loss. Let's try to plot the confusion matrix for precise version. Precise version, which was run for 4 epochs. Oh, see, now the data looks much more better. Like it is not flagging most of the queens as queen now. But now it is flagging most of half of the queens as king and half of the kings as king and the remaining as knight. So it didn't really improve it that much. Let's check the top losses. What if we tweak the minimum scale parameter? Should we increase the parameter or decrease it? Minimum scale. How much of the image to select at minimum each time? At minimum 0.3% should be selected. Now over here it is saying at minimum 0.75% should be selected. It is already a large amount. What if we increase it to something like 0.8? And now let's fine tune it. Flagging 10 queens as king. Does that mean that increasing the minimum scale decreases it? Alright, let's try to decrease it to 0.5% this time. Let's plot the confusion matrix now. It did improve a bit. So what if we decrease minimum scale to 0.3? And now let's try to run. Alright, so 0.5 is a good spot. Let's keep the minimum scale as 0.5 only. What if we increase the augmentation transform? Or should we increase the item transform resize? 468. Let's try to run it for 8 epochs now. This model is not so bad. Let's save it as just 3 precised. It's still detecting this thing as a night. And what about this other image? Night. That's the thing with knight and queens. Knight, queen, and knight. One of the queens has been flagged as knight. Okay, so this guy has also used FastAI library to classify the chess species. Let's check his notebook. He's fine-tuning it for 2 epochs only. Is getting 0.5 error rate and 1.4 for validation, 1.97 training. does LR find do? Learning rate finder. Learn or learning rate finder. I don't know what this things does. Unfreezing, it has something to do with transfer learning, I guess. I haven't yet learned how to do unfreezing and such things. If we compare the confusion matrix, this model is doing quite good actually. Okay, so this guy has used Keras and TensorFlow.